Welcome back. In this episode, we're going to continue to talk about stylometry, but instead of dealing with hierarchical cluster analysis, we're going to be talking about principal component analysis. And this is another very useful approach to take in stylometric analysis. It will use the same initial data as hierarchical cluster analysis, but we're not going to be measuring distances between objects. Instead, we're going to be using linear algebra to develop abstracted axes that will help us show where the variance in our data is. Now, essentially what we're doing is we want to plot these documents in a scatter plot. But the problem is if we're looking at 1,000 different words in these documents, that's 1,000 dimensions. And of course, we can't visualize anything over 3 dimensions. So we need to do what's known as dimensionality reduction, and PCA is an example of this. Essentially, what we're going to be doing is we're going to twist our data around to try to get the best view of it in a few dimensions. Now, principal component analysis will return to us axes that is essentially a view of as much of the variance in the data set as it can get hold of. So in some cases, the first principal component will show us about 30% of the variance in the data set if we're lucky. The second might be 8%, and then from there it goes down further and further. This is a really useful way of trying to cluster similar things together. So we're going to start by importing the necessary libraries as usual. And here what we're going to be doing is we're going to be importing the PCA module from sklearn.decomposition. That's essentially what's going to do the magic for us. Or it's not magic, it's actually just linear algebra. So what we're going to do is we're going to just use the same stuff we used from before. We're going back to our Sherlock Holmes short stories. We have story year, year color, ignore files. We'll just load all of this stuff in, and nothing really changes until we get down to line 51. Now, when you do principal component analysis, you can actually get as many components as the number of dimensions you have minus 1. But the further you get down in those principal components, the less information they actually contain, because we're essentially trying to shove as much information into the top 2 dimensions as we can, or top few dimensions. So we want to just plot this on a scatter plot with an x and a y axis. So let's just get 2 components. So what I do is I use the PCA object from sklearn, and I say, give me the top 2 components, n components equals 2. And I save this as a PCA variable. Then what I do is I do fit transform, and we saw this with the TF-IDF vectorizer before, and I'll give it that count matrix. And I'll save it as my PCA. This is a variable that you'll often see in tutorials related to these sorts of things, so I'm just going to go ahead and use that. Now, we've done the analysis, but we actually need to plot the documents. Now, this is going to look a little bit strange because we have to take advantage of the matplotlib scatterplot function, and we need to give it a few different things. The first thing we need to do is, because we're coloring the data by the year in which it was written, we need a list that contains the unique years in the data set. And we also want integers that reflect each of these unique years or unique classes. So I'm just going to say number for class is 0 and 1. And you'll see in a second why we need this. Then what we need to do is we need to make a dictionary. And I'm going to show you a little bit of new syntax here, because this will just make a dictionary where the keys are the unique years and the values are found in number for class. So essentially it's going to be 1981, and then the value for 1981 is 0, and 1982 is 1. So what I'm going to do is I'm just going to say zip unique years and number for class, and I give that to the dict function, and this will give me a nice little dictionary that contains that information. So the next thing I need to do is to make a representation for these documents that's just the integers. And I need it to be a numpy array because we're going to excuse me. I need it to be a numpy array because we're going to take advantage of some of the nice indexing functions in numpy. So here I'm just going to say np.array, and then I'm going to say year for class number, the story year s for s in short titles. What this is doing is it's just going to go through each of the short titles, give it to the story year, and then give that to the year for the class number. So what this will produce is a list of either zeros or ones according to what year the given text was written in. And if you want to play around with this, feel free to add print statements. So you can print text class to see what this looks like. And I'll go ahead and do that. And we'll go ahead and also print my PCA up here so we can kind of get a better sense of what this looks like. And I'll save this. So then what we do is we make a list of the colors. Okay? So what I'll do is I'll say for every year in those unique years, which is just 2, in fact, 1981 and 1982, give me the year color, which is up here on line 22. So it's just going to say, it's going to create a list that's just magenta and green. Then to actually plot this in a scatter plot, what we want to do is we want to just go through and say, OK, for color, class number, and year in zip colors number for class unique years, do something. OK? So it's just going to take this list of colors, which is 2 items, the number for class, which is also 2 items, and the new unique years, which is also 2 items. So we can actually see what these are by printing them out, and we might do that here in a second. Then what I'm going to do is I'm going to call the matplotlib scatter function. Okay? And then I have this really funky looking thing in here. My PCA, text class equals class number 0, and my PCA, text class equals class number 1. And I'll kind of get into what's going on here in a second. The label equals the year, and the color equals C. And I'll go ahead and add a legend, and then I'll plot it. So let's run this. So this is Python 22, stylometry 4. And what it'll do is it's going to print out what we want, and we'll take a look at that here in a second, but it's going to give us this scatter plot. Now again, we don't know what short story is what, but we do know that 1981 and 1982 don't seem to really cluster together in a meaningful way. So let's talk a little bit more about how the code is actually working here. I'll close this, and we can take a look at this. We can see that the principal components, this is the result that we got. So each document is represented on a line here. And this is its XY coordinates in those 2 principal components. And here we can see the class labels, the 1s and 0s for each document. So let's think about what's actually happening here to plot this properly. Essentially what I'm doing is I'm running the plot.scatter function twice, once for each class of document, 1891 and 1892. So here I have a list of 2 things, magenta and green. I have number for class, which is 0 and 1, and I have unique years, which is 1891 and 1892. So the first time through, what's going to happen is it's going to use class number, which is going to be 0. And I can take advantage of the fact that I have this text class variable up here, which is a NumPy array. And I want to say the text class equals the class number. So what is actually happening here is it's creating a Boolean NumPy array that is just a bunch of falses and trues. So I'll print this out so you can see what this looks like. Text class equals 0. And I'll save this, and I'll go ahead and run this over here. So this is, again, Python 22 stylometry 4. And so it's just going to print out the same things, but it's also going to show you that down here I have this Boolean array, which is false, true, 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 false, 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 true, false, 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 true, true. Here you can see 1, 0, 0, 0. So what it's doing is it's matching up trues and false based on what these numbers are. And then what I do is I feed this in to this myPCA object. So then what it does is it just goes through and it says, only look at the items that are true. In this case, these are true. And then the others are true as you move down the list. And only plot those. So then I just say, get the first item in this particular local array and the second item. And these are the x and the y coordinates. And that's how we actually plot these. So it does it for both of these. And that's really how you do the stylometry. Even though it's a little bit complicated, it's actually quite elegant. So next, what we might want to do is we might want to take a look at what this looks like when we run this on the Federalist Papers. So I'll go ahead and I'll do the same thing I did before, and instead of running the Sherlock Holmes text, I'm going to feed in the Federalist Papers. And we actually don't see anything that's new in this particular text, except now I have my unique authors are Hamilton, Madison, Jay, and unknown, and I have numbers for each class. And here, instead of just saying 0 and 1, I'm just going to go through the length of the unique authors and just generate I. But otherwise, everything is exactly the same. And I have this color dictionary for each of the authors. And you might want to make sure that you're doing this in an automated function, because sometimes you might be dealing with something with a fair number of different classes. So what I'm going to do here is I'm going to go ahead and plot it like we saw before, but I'm also going to label individual points so we know which document they actually are. So what I'll do is I'll just go through number and data point in zip, the Federalist list number, that's 1 through 85, and my PCA. So this is just saying, get the location of each of these Federalist numbers and use that as a label. And we'll use plot.annotate, which I don't believe we've seen yet. And I'll give it the string, which is the number. So it's just turning that 1 to 85 into a string. And then I'm just saying the xy point equals the data point. And I can do this because the data point that comes out of my PCA is just a NumPy array that's the x and the y coordinates. So I'll go ahead and I'll run this. I'll do Python 22 stylometry 5 PCA fed. And what we'll see is it looks like this. So now, unlike in the case where we were just looking at Sherlock Holmes, this actually makes a lot of sense. Here's John Jay over here. James Madison is mostly up here, and we can actually see all of these unknown texts seem to be more similar to James Madison, but some of them kind of exist on the border between Madison and Hamilton. So this is another view of looking at these different documents. Now, the hard thing about dealing with principal component analysis is figuring out how do you actually interpret what these x and these y dimensions mean. So the x dimension is principal component 1 and the y dimension is principal component 2, but what are they really reflecting when it comes to how language is being used in different ways? Well, in order to actually figure that out, we need to take a look at the component loadings. And these are essentially how the individual words are pulling these documents in different directions. So what this looks like is essentially the same, except instead of plotting the texts by themselves, I'm going to add the words themselves onto this plot. And this is a really cool thing. So here we have everything, except now what I'm doing is I'm actually making the dots smaller, and I'm making them a little bit transparent so we can see the words a little better. Now, we can get the component loadings out of the PCA object, not the actual fit and transformed object called myPCA. This is a little counterintuitive, but it's just how it is. So I go pca.components_, and these are the loadings. Now I also want to get the vocabulary out of this count vectorizer, which I can do with get feature name. So this is just going to say, you're looking at the 1,000 most common words. Well, what are those 1,000 most common words? Then I can actually add them to the plot using plot.annotate. So I'll say for I word in enumerate vocabulary, so give me each item in the vocabulary along with its place in the list. And then annotate that word at the xy location of loading 0i, loadings 1i. Now this looks a little bit funky, but the shape of the loadings object is a little different than the PCA object. So this will just say, for the first item in this list, which is a list of all of the x coordinates, get me the ith item. And for the second item in this list, which is the y coordinates, get me the ith item. Okay? So it's relatively straightforward, and I'll go ahead and I'll run this code. This is 22 stylometry 6 loadings. So I'll run this, and it might take a second, and here we go. And now what we can see is what these different dimensions actually represent. So we can see at 0, 0 are where most of the words are. The further a word is away from 0, 0, the more influence it has on pulling texts in a given direction. So for example, On and by are used in documents that show up here far more than they are used in documents that show up down here. Similarly, is used more often in documents on the left, and they is used more often in documents on the right. So you can actually see that John Jay uses they, their, they, or our, it, that more often than the other authors do. So you can kind of see, based on how these words are pulling text in different directions, what these axes might mean. Now, in this particular case, you can say, you might think about what is the relationship between on and by with there upon in. They might be prepositions of different sorts. So you can say that the y-axis represents the general relative use of these particular words, which is exactly what it is. So this is how you would go about interpreting the results of your principal component analysis. Now, there are a lot of things you can do, and you can really refine what you're doing with principal component analysis and stylometry in general by looking at specific sets of words, different numbers of words. You can even look at different principal components by looking at the third or the fourth dimension, and so on and so forth. So that's how you actually do a little bit of basic stylometry in Python. In the next episode, we're going to move on. We're going to talk about the GenSim library, where we'll be talking about topic modeling and a little bit about word2vec. So I hope to see you next time. Thank you.